Hi, welcome to another session of the Potter's Roundtable from Washington Street Studios in bucolic Bolivar, West Virginia. I'm Phil Bernberg. Last time we talked about building your own gas-fired raku kiln. This was part of our series on kilns and firings. And today we're going to be we're starting a new session on solving problems. And so this is going to be talking about kiln performance problems.
Welcome to the Potter's Roundtable, a monthly podcast where we share our passion for the ceramic arts and a collection of topics specific to potters. Remember to subscribe so you don't miss a single episode. Enjoy the show.
The problems can be there are really three sources to the problems. They can be something inherent in the kiln design, in the construction of the kiln. They can also be a piece of the kiln or the equipment that you're using that fails during a firing that causes a problem. Or it could be part of the actual operation of the kiln, how you actually run the kiln. In some cases, it's several of them. Anyway, we'll point this out as we go along. And so what we're going to do, I thought, is we'll talk about the three major kinds of firing that you're probably familiar with: electric kilns, gas kilns, and wood kilns, in that order. So we'll start with electric kilns. In electric kilns, basically, you generally don't have what I'd call design problems. Most electric kilns are fairly well designed and fairly well constructed, so there aren't sort of fundamental features that are part of the design that can cause problems. So most of what we're talking about is operational problems or equipment failure problems. So let's go down a list of some of the things that can happen when you're firing an electric kiln and some of the causes and how you can remedy them. Well, one of the first things, obviously, is you turn on the kiln, you go to start the kiln, and it doesn't heat up. And the obvious thing is there's no power to the kiln. Now this could be an equipment problem. It could be, for instance, that there's a fuse or a circuit breaker which has tripped, so you need to check it. By the way, as you're probably aware, electric kilns should all be located on their own separate line and their own circuit breaker. They shouldn't be on a line that's part of some other piece of equipment or some other use for it. It also could be that the relays, there's a difference between manually operated kilns and electronic controller kilns. On manually operated kilns, you have switches or knobs or dials that turn on the power to the elements. On the electronic controller, you still have switches, but they're basically electrically operated switches, and they're called relays. And so in either case, if the manual switches are not working properly or the relay is not working properly, then even though it looks like you have power to the kiln, when you go to start it, nothing happens because no power is actually getting to the elements. From an operational point of view, one of the things that can happen is if the kiln has a kiln sitter, is you need to check to make sure that when you loaded the kiln and set it up for the firing, that you pushed in or restarted the button on the kiln sitter, that it hadn't tripped. Because just flipping the arm up and hooking it doesn't restart it. You have to manually push the button in. Also, something that I found that people tend to forget is that if your kiln sitter is one of the newer kinds that has a timer on it, then you need to make sure that you put time back on the timer. If everything else is working properly and you haven't reset the timer and given it at least some amount of time, the kiln will not start. Okay, so let's say you have power and you start the firing, but now the heat up of the kiln seems to be very slow. It just doesn't seem to be getting hot very quickly. This is kind of a classic sign of aging elements. As electrical elements get older, the resistance of the elements increases, and so with the same amount of power applied to them, they heat up less efficiently or less rapidly. So it could be simply that this could be an indication that your elements are getting aged. And you probably would know about this. You'd have an idea of how many firings you'd done or how long it had been since you'd changed your elements. The other thing is, if it isn't age on the elements, it could be that one or more of the elements are not working. And if you don't have the full set of elements working, then the kiln can't go up in temperature as it's intended. So even one element can slow down the temperature rise a lot. So this is where, again, you would need to check for either a broken element or, again, a bad switch or a relay. There might only be one relay or one set of elements out of all the elements in the kiln which is not working. That's enough to slow down the heat up a lot. Okay, so now at the other end of the firing, maybe the kiln shuts off early. Well, the obvious thing is, of course, could be a power failure, but it also could be related to the kiln sitter if you have one. One of the things that can happen is sometimes the cone that you put in the kiln sitter itself, if it has a little manufacturing defect in it, it might break prematurely, so that instead of bending as it gets softened and shutting the kiln off when it's supposed to, it actually just snaps. And when it does that, then the kiln sitter shuts off early and the firing ends early. Another feature that people may not be aware of is that the kiln sitter actually has several adjustments that are possible on it. You can adjust the sensitivity of the kiln sitter so that the arm on the kiln sitter has to move a certain amount before it will actually trip the switch. And if the kiln sitter is set so it's too sensitive, in other words, that too little movement will shut it off, then you need to adjust that. And that could be part of the problem. The fact that maybe the cone, the temperature was increasing, the cone was starting to bend, but then with just a slight amount of movement, the kiln shut off, rather than going to more bending of the cone before the kiln sitter shuts off. Another feature, of course, I mentioned just before is the fact that also the timer might have run out. I've seen this a lot at community studios where you have a range of people setting up the kiln, and they'll forget to put they won't know how long the firing is going to last, so they'll put 5 hours or 6 hours on the timer, and then it's a 12-hour firing. So you have to make sure that the first thing is to check is, did the timer run out? And also another possibility, maybe not that common, but I've seen it happen, is somebody just puts the wrong cone in the kiln sitter. They're firing to cone 6 and they put in an 06 or something in the kiln sitter, or the wrong cone, and of course then it'll shut off prematurely. Another thing that can happen is, and this is primarily with electronic controllers, is that the temperatures that you see don't seem to match the cones. In other words, it looks like the temperature reached what it was supposed to reach, but the cone didn't shut off, or vice versa. There's a feature on most electronic controllers called a thermocouple offset. And basically you can adjust that. So you can compensate for the fact that maybe the thermocouple is not reading true, and you can adjust that a little positive or negatively. You can tweak that. But this is only on electronic controllers. Another feature sometimes that you'll see is a non-uniform temperature distribution in a kiln. Most noticeable, you'd see that on the effect of the glazes. You might see some glazes in a part of the kiln that are underfired or overfired. Well, first of all, with electric kilns, this is a normal occurrence unless you have a downdraft fan on the kiln. It's perfectly normal for an electric kiln to be slightly hotter at the top and cooler at the bottom. In some cases, it can be by at least a cone difference, or possibly even slightly more. So one of the things to consider if you don't have a downdraft fan would be you can partially offset that effect by the way you load the kiln and the way you space the shelves. So for example, if the bottom tends to be a little cooler in your kiln anyway, then you wouldn't want to put closely spaced shelves at the bottom, and you wouldn't want to densely load those shelves, because that means that all that increased pot loading and the closer spacing is going to require more heat to get hot than the upper part, which is maybe loaded more loosely. So you want to counteract that. You want to tend to load the bottom more openly, and the top that's going to be hotter more tightly, and that will actually tend to even out the temperature profile. The other thing is that this could also be an indication of something related to the equipment. It could be that the elements in one particular part of the kiln, the top or the bottom, are aging or wearing out sooner than the others, and so therefore the bottom might be excessively cool, or even the top might be cool, because the element in that particular location is not getting hot. There's no guarantee necessarily in an electric kiln that all the elements are going to age at the same rate. Even though you install them at the same time, for example, or if it's a new kiln, there's still no guarantee that they're all going to age exactly at the same rate. Somewhere, one of them is going to be first in terms of aging or wearing out. And that could also cause sort of a difference in the temperatures within the kiln. Finally, one other thing to think about is the fact that if you have an electronically controlled kiln, and it only has one thermocouple, then the whole controller is only sampling one point in the kiln. So the controller is running the whole kiln based on the temperature that it sees at that one particular point. And so and there's no way for it to compensate for it. If the top is hotter or the bottom is cooler, all it can do is run the kiln based on that one spot. Whereas if you have the type of kiln that has 3 thermocouples, those controllers are designed to compensate so that the kiln controller is monitoring all three thermocouples. And if it sees that the top or the middle or the bottom is lagging behind the other two, it will increase the power to those two and tend to keep more of a balance. Glaze runs, and again, this is something you judge from the glaze. Well, basically, if you see excessive glaze runs, and you know, for example, that it's not due to the fact that you have a mysterious formula or something that isn't working correctly, basically the glazes have been overfired. And other than intentional overfiring, one of the causes that exists is the fact that the firing may be too fast. We've talked about this before, is the fact that when you're firing to a particular cone, like let's say you're waiting for a cone 6 to go down, because cones respond to heat work, that is a combination of temperature and time, if you're firing quickly, that is less time, to get the same amount of heat work, you have to have more heat or a higher temperature. And it's 20 degrees or 25 degrees is not uncommon for a kiln to overshoot sort of during a fast firing. That's enough to make some glazes run, especially earthenware glazes and also cone 6 glazes tend to be more temperature sensitive. They have a narrower range than cone 10 glazes, and they're more likely to run with a slight overshoot. And again, then the other possibility is you might have put the wrong cone in the sitter, and so basically it was overfired because the final controller was not set to the proper cone. Also, if you have glaze runs, one of the things that can happen with a kiln, another thing that can happen with a kiln sitter, which is, by the way, one of the reasons why I really don't recommend that you fire using a kiln sitter as a controller. It's a nice safety device, but you really should be firing by observing cones. And one of the problems that can happen, I'll draw a little something on the board here, is the fact that when you look at the end of the kiln sitter, there are two blades that sort of stick out from the end. This is the ceramic tube that projects into the kiln. There are two ceramic blades, and the cone, and then there's this movable rod that moves up and down, and you set the cone across the blades like that, and then it bends, it moves down. Well, one of the things that can happen is sometimes when the cone starts to get soft, it can, and if these blades, these metal blades, have started to corrode, when it starts to bend, it can actually stick to the metal. And in order to bend completely and trigger the switch, it has to bend down to a certain curvature. And if it sticks when it first starts to bend, it can't bend. It would have to get a lot hotter to the point where it's really soft and it will almost droop under its own weight. Well, by that time, the kiln is overfired. So it's possible just that if the cone just happens to melt in those spaces or get and stick, the kiln will overfire. So this is just one more thing that can go wrong with a kiln sitter. So they're great as a possible safety device. By the way, not to go off on this track, but this is another reason why in more recent years they put a safety device on the safety device. That is, there's now an electric timer on the kiln sitter. So if the kiln sitter doesn't shut off, the backup system, the timer, will shut it off. Pretty soon there's going to be a backup for the backup, but not yet. Okay, so then also with glaze runs, you might see a case where instead of having glaze runs, let's say at the top or the bottom or all over the kiln, they might just be at the edges of the shelves. This is basically the same symptom. It means that the pots that were on the edges of the shelves got too hot, and it might be simply that they're too close to the elements. You generally don't want to have pots. I usually try to stay at least an inch or more away from the elements. The further the better, because if you think about it, the heat is coming from the outside, the walls, and coming in toward the center of an electric kiln. And so the pots that are nearest to the elements are getting the hottest, the fastest, and they're getting the hottest of all the kilns. There's always going to be a certain temperature difference between the walls where the elements are and the center of the kiln. And so if they're too close, basically the pots get overfired. Then the final thing is that you may see occasionally accumulating on your kiln after a number of firings, if you see a lot of metal corrosion, or if you see actually crumbling of the bricks, this is an indication that your kiln is not vented properly, that the corrosive fumes that are produced during the firings, mostly during the bisque firings, but the corrosive fumes are not getting out of the kiln. And what happens, the strange thing, or it seems strange, aside from seeing corrosion on the metal parts, the hinges, and just anywhere around the metal frame, is when you look down at the top of the kiln, and let's say, I'm exaggerating the wall thickness, but there's the wall, this is the wall of the kiln, so this is the outside. when the bricks start to crumble, they don't crumble on the inside, they start to crumble close to the outside, just inside the metal shell. And if you start to see that, that's because the acid fumes that are coming out of the kiln, when they meet the air on the outside of the kiln that has moisture in it, it forms acid and starts to attack the bricks. So if you start to see this crumbling just inside the metal shell on the outside of the kiln, that's a good indication that you're really not venting your kiln properly. Okay? Okay, so those are some problems with electric kilns. Let's move on to gas. That's not all of them, by the way, but these are some of the more common ones. There's almost no limit to the number of problems you can have, but these are some of the more common ones. Let's talk about gas kilns. Well, with gas kilns now, you can actually start to have design problems. Not so much with commercially produced gas kilns, but since gas kilns are one of the types of kilns that potters fairly often design and build themselves. And so it's very possible to have basically design faults or less than optimum features in the kiln. So now with gas kilns, you can actually have some design problems as well. One of the common problems that you see with gas kilns is, again, a slow temperature rise, which basically means you're not generating enough heat fast enough. It could be equipment related. It could be that the burners are too small, or it could be that there are too few burners. There aren't enough burners for the kiln. It could be that the secondary air inlets are too small. In order to completely burn the fuel in a gas kiln, even if you're using a burner where you're putting in air through the burner, a Venturi burner or a burner with a blower, you also need additional air called secondary air to complete the burning of the fuel and generate enough heat. So if the inlets or the opening around the burners is not large enough to let in enough air, then you can't get complete burning, you won't generate enough heat, and you get a slow heat up. So it could be that the air inlet, the places where the air can get in, are too small. It could also be, now with most gas kilns, you have some kind of a chimney, or there's an exit flue. There's a hole where the gases leave the wear chamber and enter into the vent or the flue or the chimney. And if that opening is too small, it basically chokes the kiln. The hot gases are trying to get out, and they can't, because it's like the old thing with the theater during a fire and everybody packs up at the door. Well, the gases are trying to get out. They can't get out through the small opening, and this backs up into the kiln, and now it can't draw more air in because the gases can't get out. So that can be just basically, that can be a design problem, that when the kiln was built, for instance, the opening to the exit flue was not large enough, or the air inlets were not large enough. The other thing can also be is just the way the kiln is being operated, basically maintaining the correct balance between gas and air. If you're trying to maintain, let's say, a slight reduction, there's a tricky balance there between having not quite enough air so that you maintain a reduction atmosphere, but enough air so that you're still burning enough of the gas to produce enough heat to get the temperature to rise. And this is true for any fuel-burning kiln, where you have to manually, unless you have an automatic controller, which is not that common for most people, but you have to manually maintain this control between the air and the gas, or the air and the wood, which we'll talk about in a minute. Unwanted soot formation. If you're trying to get reduction in a gas-fired kiln, unless you're purposely trying to produce carbon trapping for, let's say, a carbon trap chino glaze, you don't want to produce soot. When you see soot being produced, it means you're getting into too heavy reduction. The reduction is way too heavy. You want to produce carbon monoxide, which you can't see. You don't want to produce soot. And so when you're producing soot, basically what it means is you're not burning the gas efficiently. You're wasting a lot of gas. And therefore, if you're wasting gas, you're not generating enough heat. And therefore, the temperature won't rise. Stalling. This is another during the heat up. This is another fairly common occurrence. But it goes back, it's the same thing as a slow temperature rise, only in this case, what the term generally refers to is you're heating up the kiln, you get to a certain temperature, and maybe the temperature rise has been great up until that point, and all of a sudden it stops, it slows down, maybe the temperature even starts to drop a little bit, and you don't know why. Well, first of all, there's a fundamental law of physics that says that as something gets hotter, it wants to lose heat faster and faster. So it's kind of like running up a hill, firing the kiln is kind of like running up a hill, only the hill is getting steeper as you're firing it. What that means is that if you just put a certain amount of heat, you can plot this. So this is the temperature and this is time. If you just put a certain amount of heat into a kiln and turn it on and let it go, it'll heat up quickly and then gradually it'll slow down and slow down and slow down and basically almost stop increasing in temperature. What's happening is, as you're getting higher in temperature, the heat is being lost faster and faster. So in order to keep the temperature rising, you have to put in more and more and more heat because the heat is being lost faster and faster and faster. So you have to keep up with that. So again, what this usually comes down to is the rate of burning. You have to turn up the gas so that you're burning more gas, and you still have to maintain the correct balance between the gas and the air so that you're burning the gas as efficiently as possible to produce enough heat. But it basically comes down to the fact that you're not producing enough heat fast enough. The heat is being lost faster than you're putting it into the kiln.
We hope you're enjoying the show. Please take a moment to leave a 5-star review on your podcast platform of choice. It really helps new listeners find the show. Don't forget to subscribe to receive updates as new episodes are released. And if you'd like to support the video and podcast production of the Potter's Roundtable, become a patron. Go to patreon.com and search for the Potter's Roundtable. Your support will help us achieve our goal of creating a digital library spanning the ceramic arts for use by educators and artists alike. Thank you for your support. Now let's get back to the show.
Okay, so maybe you notice that while you're firing with propane, that the gas pressure is dropping. Well, what this usually means is that the liquid level of the propane in the tank is getting too low. Propane in a tank, when you buy the tank, is not a gas in the tank, it's a liquid. And when you open the valve on the tank and let some gas out, the liquid boils and produces more gas. So when the level in the tank is getting too low, it means, yes, you are running out of gas, but it can't boil fast enough and produce enough gas to maintain the pressure. This can be aggravated because in most cases your tanks are sitting outside. So if the temperature is dropping or the temperature is low, then the situation will be aggravated because then the liquid tends to boil even less vigorously and produce less gas. So basically, it means that it's a warning that your gas supply is getting too low, basically. Failure to reach peak temperature. Okay, maybe you've gotten the kiln up to fire pretty well. It's up to most of the point, and you're getting close to the end of the firing, let's say typically cone 10, and you can't quite get there. This goes back to some of the same issues we talked about already. Basically, it still means the fact that you're not producing enough heat fast enough. So it could go back to the vent. This is where sometimes it shows up that your burners are too small. The burners might work great up to a certain point, but now at this extreme high temperature, you need to be producing a lot of heat, and the burners simply are not capable of producing it. They may be too small, there may not be enough of them. Again, like we talked about before, the secondary air inlets may be too small. You simply may not be able to get enough air into the kiln to burn all the gas efficiently, and the flue opening may be too small. You may be choking the exit gases. It goes back to the same issues we talked about. You need to be burning enough gas fast enough, and you need to maintain control over the gas and the air balance. It's possible to actually put way too much. What happens a lot of times when this happens is that people will turn up the gas again, and they end up putting too much gas in the kiln, and there still isn't enough gas air to burn it, so they turn up the gas, and the temperature actually drops because they haven't provided enough air to burn that additional gas efficiently. Okay, hot cold spots. So now you notice you've survived the firing and you think it went well, and now you open up the kiln and you notice there are hot and cold spots in the kiln. And basically you judge this by looking at the glazes. Some of the glazes might look underfired, some of them look overfired. This could be a design feature, especially with kilns that are built by the potter or by the user. In some cases, the kiln has not been designed to properly mix the air and the gas. Again, to really generate the heat, the kiln has to be designed so that when the air and the gas enter the kiln, there's a place and a certain amount of time for them to mix and thoroughly mix to get efficient burning before the gas hits the pots. And if the kiln isn't designed properly, doesn't have that space or that combustion area, then you won't get good mixing and you won't get good combustion. There could also be what are commonly known as dead spots in the kiln, and that is where the shape of the kiln or the location of the burners creates spots in the kiln, typically corners, where the flame simply does not go into the corner and heat it up. There's no reason, for example, logically, there's an awful lot of wishful thinking in pottery where people think that because something should happen, it does, but it doesn't. And so it's very common, if I look down, for instance, at the top of, this is like looking down on the top of a kiln, there's no reason for a flame to go into a corner and turn right and do that. The flame is going to tend to want to, it's basically a blind corner, so the flame is more likely to want to do that. Let's say this is the exit. So the flame is headed for the exit. It's not going to do that. It's going to take the shortest path to the exit. And it might do this, but then what happens is, if it doesn't really fully get into this corner, that becomes a cool corner or a dead spot. There isn't really a lot of gas circulation or flame movement into that spot. That's a dead spot. It could also be related, in addition to the design of the kiln, it could be contributed to by the way you stack the kiln. With a gas kiln, basically you have a river of flame that's flowing through the kiln, and you can affect where that flame moves and how it flows by how you locate the pots. So it's possible, for instance, to have a wall of big pots blocking the flame from getting to the pots behind it. So when you're loading the kiln, one of the things that you need to keep in mind is you're basically creating the path for the flame to move through the kiln and between the pots. So how you stack the kiln, how you space the shelves, and how you place the pots controls to a great extent where the flame is going to go, and therefore where it's going to heat better or worse. Okay? Okay, poor reduction of glazes. You may notice also that some of your glazes, and especially this, people are oftentimes they're disappointed, especially with glazes like copper reds, that they don't come out the way they're supposed to. And copper reds, it's usually pretty obvious whether they're reduced well or not. One of the major problems with a lot of glazes is people don't realize that you need to do a fairly heavy reduction early in the firing, long before the glaze starts to melt. I mean, for instance, here with our little gas kiln that we fire here at the studio, for copper reds especially, I start the early reduction at cone 012, which is a little earlier than maybe some other people do for their kilns. But for this kiln, I found I need to do that, and I hold it for about an hour. I need to do that to get thorough reduction, that is reaction of the chemical atmosphere. Remember, we talked about atmospheric firings. So I'm allowing the reducing atmosphere of the kiln to react with the chemicals on my periodic table, which is no longer here, and produce these colors. So the reduction has to be long enough and heavy enough to give me the reduction. And also the other possibility is, even if I do that, if I don't maintain adequate reduction during the rest of the firing, it's possible to reoxidize the glazes to a certain extent. So I have to reduce the glazes early in the firing, long before they start to melt, and then I have to at least provide enough reduction to maintain that state so that they don't reoxidize. Non-uniform reduction, not so much that did I get it or not, but it doesn't seem to be uniformly positioned around the kiln. This kind of goes back to the same idea about the hot and cold spots. It could be that I'm getting poor mixing of the gas and the air. So that could be the design of the kiln, and it could be, again, it goes back to stacking. So the same conditions that can get me hot and cold spots can also contribute to non-uniform reduction. I can get spots where I'm not getting adequate flame to it. I'm not getting good reduction conditions. Reoxidation, it's also possible that maybe I was able to achieve great reduction during the firing, but the pot still came out looking oxidized. Well, one of the things to look at is, especially with a lot of kilns that are constructed by the potter or the user themselves, oftentimes they don't have a regular door that's swinging on hinges. The door basically is stacked bricks. And so you have to make sure that the bricks, that the door is tight, and also that when the firing is closed, that you seal up the burner ports, because as the kiln cools down, it tends to draw in air, and so you can get streams of air going into the kiln, hitting hot pots, and that will reoxidize them. So you also need to make sure that the whole kiln is, this goes to the kiln design, is the whole kiln itself tight? Are there cracks and spaces between bricks in various parts of the kiln where air can be drawn in during the cooling and hit the pots? And finally, high gas usage. This is something you might notice after the firing. You're like, wow, I used a lot of gas for that firing. This goes back to all the same issues we've talked about before. The control of the gas and the air, so that you're balancing the amount of gas you have at that time with the amount of air you need to get efficient burning without putting in extra air. You can actually, it's possible to put in a lot of extra air. If you're going to a certain temperature, it takes a lot of heat just to heat up the air. Forgetting about whether you're getting reduction or oxidation, you're basically bringing in cool air. So you can have, it's possible to have way too much gas. It's also possible to have way too much air. And both of those will give you inefficient temperature rise. And again, this goes back, what I mentioned before also, this goes back to air supply and features of the kiln, such as, does the kiln provide for enough air inlets and that sort of thing. Okay? So those are some of the common problems with gas fire. Now let's finish up here and talk about wood kilns. Wood kilns, of these three, they're probably the most common types of kilns to have design problems, because you can't buy really commercial wood kilns. If you have a wood kiln, chances are somebody you know or somebody you hired has built it for you. And I've seen a lot of wood kilns that are basically have some kind of feature or features in them that are less than optimum. So it's fairly common to have features in a wood kiln that it may not be so much equipment failure, because usually wood kilns, especially, you don't have a lot of plumbing going on and things like that can fail. So yes, you see, a lot of times you have kiln design problems or you have operational problems. So again, one of the common problems is the slow temperature rise. And this basically, if you think about it, all it means is I'm not putting in enough heat fast enough. I can't get the temperature to go up. This could be a combination of equipment or operation. In terms of operation, now you have to think about, for instance, what's the quality of the wood you're burning? Is the wood wet? If you're using wet wood that hasn't been thoroughly cured or dried, it takes heat to dry out the wood. And before the wood can burn, it has to get dried out. So it takes a lot of heat to evaporate that moisture out of the wood. So that's a waste of heat, which is going to evaporating water and not raising the temperature of the kiln. Is the wood too large? You have to consider the size of the wood. In order to get the temperature to rise in a wood kiln, the wood has to burst into flames and burn fairly quickly to yield its heat. And so if the wood is large, it tends to burn more slowly. It might burn longer, but it might not produce enough of a burst of heat to get the temperature climbing. And related to this is the stoking cycle. How often are you putting in the wood? And every single kiln has its own sort of preferred stoking cycle. Not only the size of the wood maybe, but how often you put it in and how much you put it in. And the idea is you want to put in enough wood so that it catches and starts to burn fairly quickly, and so that you get this burst of heat that comes off it, and then it'll burn, and then the heat coming off of it starts to slow down, and then at some point, when the heat coming from the wood is starting to slow down, it's time to do another stoke and put in some more. So the heat that you generate with a wood firing tends to be very cyclical. You'll get a burst of heat that'll come off of it, the temperature will go up, and it'll start to slow down, and maybe even drop a little bit, and then you put in another load, and so you end up with a heating curve that instead of looks like this, it tends to look like this. And each one of those fluctuations corresponds to a stoking cycle. So it could be simply the operation. You're not stoking often enough, for instance, to maintain the heat rise. But there also could be equipment problems. One of the things that's different about most wood kilns compared to gas kilns or electric is that almost all of them are made with hard or dense fire brick, which you need to have that in order to resist the corrosive effects and the slag and the ash that's going to accumulate. But hard fire brick is a terrible insulator, and it absorbs a lot of heat. So with a wood kiln, you've got a lot more mass of the kiln that has to get hot before the pots and everything else inside them can get hot. So there's just a lot more that has to be heated than with most gas kilns. Most gas kilns, or a lot of them at least, are built with either refractory blanket or they're built with insulating fire brick, which doesn't take as much heat to heat up the kiln. Then you can also have design features. For instance, the firebox might be too small. They simply might not be able to hold enough wood to generate enough fast enough. Or it goes back to, it's always an air or a fuel problem. So if it's not a fuel problem, then maybe the chimney is too short. If the chimney is too short, then the draft that it creates, the pull on the firebox, is not enough to bring in enough air to burn the wood quickly enough. Or the air inlets could be, maybe the chimney is tall enough, but the holes where the air actually come in, the air inlets are too small to allow enough air to get in. And so basically the kiln is sort of choking itself and it can't get enough air. Okay, so let's say you start to get, and yet these are some of the same features or the same symptoms that you see with a gas kiln, but with somewhat different, a little different interpretation as far as the cause. So now again you get stalling. This is very common with a lot of wood kiln designs. You get up to a certain temperature and you're getting close to the end maybe, and all of a sudden the temperature just refuses to rise, and you're throwing wood in and you're playing with the chimney and playing with all the controls you have, and nothing happens, and maybe even the temperature is starting to drop a little bit. Well, the underlying reason is the same. You're not producing enough heat. However, whatever it takes to do that, you're not producing enough heat. So it could be the fuel-air balance. It could be the size of the wood, how often you put it in, how much air you're providing, how often you're stoking the kiln. But again, as we mentioned with the gas, this is a natural feature. This goes back to a law of physics that the hotter something gets, the faster it wants to lose heat. So even under ideal conditions, if I was throwing in the same amount of wood from the beginning, the kiln is going to tend to heat up like that, if this is temperature and this is time, which means that at first it's going to heat up quickly, and with the same amount of wood going in, it's going to heat up slower and slower and slower, because the heat is being lost from the kiln faster and faster and faster. Just as an aside, by the way, if you've ever wondered about how efficient a wood kiln is, or even a gas kiln, in terms of how much of the energy, the heat, or the fuel that I put in actually goes to heat up the pots, it's in the neighborhood of 5%. It might be as drastically high as 8%, but it's in the neighborhood, usually typically around 5%, give or take 2%, which means that 95% in round numbers of the heat that you're putting in, 95% of the wood, 90% of the gas, 95% of the gas, is doing nothing but heating up the shells, heating up the kiln, and going up the exhaust. So there's a lot of opportunity to heat to be lost, and you have to make sure you're putting it in fast enough. Okay, and then finally you have the same issue that we had before with the gas. We talked about failure to reach peak temperature, and this is the bane of every person that wood fires. It's 4 o'clock in the morning, you're getting close to the end of your shift, and you're waiting for the cones to drop, you're waiting to reach the final cone 10, whatever cone you're shooting for, and it just won't do it. It won't get there. It's the same problem. You're not producing enough heat fast enough to keep the temperature rising, because this hill that you're trying to climb, the hill has gotten steeper. You're running up a hill that's getting steeper all the time. And so at this point, at this high temperature, the kiln is losing heat really fast. And so you have to be able to get a lot of heat in there very quickly to actually gain temperature. So it could be the wood quality, it could be the stoking cycle, but basically it means you're not burning enough wood fast enough. And all the other things we talked about, the air inlets may be too small, the firebox may be too small, the exit flue may be too small, the chimney may be too short. It still comes down to, for whatever reason, and there are a lot of contributing factors, you're not burning enough wood fast enough. Okay, well then you have after the firing, then you maybe have the problem of, yeah, I'm burning the wood so fast, I'm using an enormous amount of wood for the firing, I'm wasting wood. Well, this again is control. This is achieving the right balance between the right amount of fuel and the right amount of air and the right timing so that you're getting efficient burning. It's basically controlling the draft. Okay, and again, there are also a lot. This is where also a lot of design features come in. There are a lot of different designs and arrangements for wood kilns, and some of them are a lot more efficient than others. Certain firebox designs, certain firebox types are a lot more efficient than others. Certain arrangements are a lot more efficient, and it just comes down to basically the fundamental design of the kiln itself. And there's a wide range of efficiencies that are inherent to certain designs. Non-uniform temperatures in the kiln. Well, this is like the gas. A lot of that is influenced by the stacking. Here we have, again, another river of flame passing through the kiln, and I can modify and change where the flame is going by how I place my pots. So the stacking, the shelf spacing plays a key role in determining where am I directing the flame, or where am I allowing the flame to go, or where am I preventing the flame from reaching. Okay? And again, there's a certain, just because of the way heating works, it's normal to have a certain temperature gradient, especially in wood. A lot of wood kilns, for instance, are tunnel-like. And it's very normal, and it makes sense, that as you get further and further away from the source of the heat, the firebox, the temperature is going to get lower. That's normal to have that normal sort of temperature gradient. But you can compensate for that to a certain extent by how you load. And in some of the designs, like some of these longer tunnel designs, they compensate for it by actually having additional fireboxes or additional places located down the tunnel, so that when the temperature drops to a certain point, because it's starting to get too cool, it's too far away from the firebox, you have a new firebox or a new place where fuel is put in to add more heat. But stacking, even if you don't have that, stacking still can help a lot. Oxidized areas, which you notice after the firing, that again, some of your flashing is not as good, or some of the glazes are not as good. The same issues as with the gas kiln. Is the door tight? You don't have burners in this case, but is the door tight? Is the whole kiln tight? The whole kiln design, is it tight? And also, one of the things that some people don't think about is when you're stoking the kiln, you don't want to leave the door open or the stoke door open too long, because you're allowing, in addition to throwing the fuel in, you're allowing an enormous amount of air to be sucked in through this relatively big opening. So normally you would have small controlled air inlets, and the chimney is pulling in the air through those inlets, and it's mixing with the fuel and burning it. The minute you open the stoking door, you have this big area, but you're sucking in additional air. And so if you leave that open too long, you've got a blast of air that's hitting the pots, which can cause oxidation if the pots are very close to the stoking door. Unmelted ash on pots, basically, you end up the firing and you've got this crusty looking volcanic lava. Some people like this, but you don't, let's say. Well, it could either mean that either you didn't reach enough temperature, you didn't get hot enough to actually melt the ash, so that the pots got sticky and the ash stuck to them, but not enough to melt. Or it could be that you produced ash too late in the firing. You may have gotten enough temperature, but if you're making a lot of ash late in the firing, there simply may not be enough time for it to melt. So one of the things I know when I've been involved with wood firings is, maybe early in the firing, you make a point of sort of tossing the wood in so that it purposely lands and lands on the wood and makes kind of a poof of ash that gets carried back into the pot. And as I get closer to the end of the firing, I'm a little more gentle with the way I stoke, trying not to create a big puff of ash, because if I know I'm getting close to the end, there won't be time for that ash to melt. So I'm a little more cautious when I stoke toward the end, so that I don't create that big puff of ash. So I guess that's sort of a summary of all the problems. And as you can see, there are a lot of potential problems, and you might wonder how anything ever gets fired decently. But the point here is that all these problems are solvable. First, you want to diagnose the problem and figure out what exactly is the cause, and then you can either change the firing procedure, or you can make repairs if it's an equipment failure, or the most extreme case might be the fact that you have to partially or completely rebuild the kiln. So there are answers to all these problems. You may not like the answer, but there are answers to all of them. Okay, well, we hope this discussion has been useful today. If you enjoyed it, please like it and subscribe to our channel, and share it with your friends and other potters, because this helps our videos get found on YouTube. We know that this was a lot of information in a short period of time, so if you want to hear it again, listen to our podcast version of the presentation. Search for the Potter's Roundtable on your favorite podcast platform. If you'd like to support our educational outreach efforts and consider becoming a patron, go to patreon.com and look up the Potter's Roundtable. Finally, check out our website, www.hfclay.com. The next topic in this series will be Chapter 18, Defects in Fired Clay. Thank you for visiting with us today.
The Potter's Roundtable is brought to you by Washington Street Studios and our patrons. If you enjoy the show, please subscribe, give us a 5-star review, and tell your friends. If you want to learn more about Washington Street Studios and shared studio memberships, please visit our website at www.hfclay.com. Thank you, and we'll see you again next time on the Potter's Roundtable.